Great. So as everyone who's been to sea will know, that half the cruise is spent coming up with the acronym, and there's a Google Doc with about 100 different acronyms, and somehow this was the one that floated to the top. So yes, excuse the torturous acronym for the experiment, but it's fun to present it. Before I start, I want to thank very much Josh Russell, who was the senior scientist, the chief scientist on the ship, on the Langseth when this experiment was actually deployed. And he provided several of these figures and slides and lots of pictures. So this experiment, this cruise that I'll be describing, is part of my NSF career grant. So this is all funded by NSF and is all enabled through the Ocean Bottom Seismic Instrument Center facility, which is the national facility that operates the Ocean Bottom Seismic Instrument Pool. I saw John Collins, who is the PI of that facility, is on this call, and I'll be directing later questions about instrumentation to him. So this experiment is in the vicinity of the Galápagos Triple-junction, which I'll show in a little bit more detail in just a second. This involved a 31-day cruise that took place in September and October of last year. We had 8 days of transit. They left from Scripps, 8 days of transit down to the deployment area, deployed all the instruments within a couple of weeks, and then we had some extra time for 4 days of multi-beaming around some patches that I'll show you shortly, and then 5 days more transit back to Punta Arenas in Costa Rica to switch things around for another cruise that piggybacked or went back to back with ours. And the recovery is coming up in just a few months. So I don't have any actual data from this experiment yet, so I'll be describing the goals of the experiment and something about what they did on board. So the overview of this, and here this is actually not quite the final array design. There was some reorganization mid-cruise, but essentially you get the idea that this experiment instruments two branches of the Galápagos triple junction, one on the East Pacific Rise, the Pacific Cocos Spreading Center, and one at the Cocos Nazca Ridge between the Nazca and the Cocos Plates. So this allows this instrumentation of two new mid-ocean ridge functionally doubles the coverage that our entire community has ever had for broadband ocean bottom seismic coverage of mid-ocean ridges historically, which is kind of amazing. We ended up deploying 44 broadband OBS instruments. We had 45, but one didn't work quite right. And then there was multi-beam mapping, and among the other important goals were training a new generation of scientists, at least one of whom, Crystal, is also on this meeting I saw. So this was the science party. Josh Russell, as I said, led the science effort, backed up by Anant Hariharan and Will Fraser as the co-chief scientists. We had 7 other grad students and 2 undergrads along as part of the science party, and 4 techs to assist with all the ocean bottom seismic instrument activities, and then 4 techs from the ship operator from the Langseth. And you can see a happy bunch of people staring out over the Pacific Ocean. This was me. I was not on the cruise because on the day, literally the day that the cruise set sail, my daughter Noah was born just over 10 months ago. And so I was not able to actually participate in this cruise, even though I had planned it for the previous 4 years, but happily I'll go on the recovery. So just to mention that this experiment leveraged, and the cruise took place on the Marcus G. Langseth, which is owned and operated by Lamont Doherty Earth Observatory. This is a storied vessel, which is sort of one of its kind. It goes back 30 years in time. Its end of life is technically now. It's actually very recently had some engine issues that mean its end of life may be sooner than we'd all hoped. But it's a unique vessel because it's the only vessel in the entire UNOLS fleet that's capable of high resolution active seismic experiments with up to a 15-kilometer long streamer that can that can allow for shots that penetrate deep into the mantle, which is pretty unique. We didn't leverage any of that capability, however, because we were just dropping broadband OBSs. I am given to understand that our cruise, together with the cruise that, as I said, followed right on from us, made UNOLS history with the volume or tonnage of material that was actually loaded onto the ship. It was, in American parlance, 139,000 pounds of gear with 73 OBS instruments and 42 ocean bottom magnetotelluric instruments. as well as all the stuff that goes along with them. This took apparently 80 crane lifts to actually get all this on board, and was a pretty wonderful feat of deck engineering, I think mostly led by Hannah Brewer, organizing all this stuff on board. So yeah, pretty impressive effort all round. This was the original. Actually, this was very close to the final deployment plan after we moved some things around. You can see we come in from the northwest, and then first deploy array A across the East Pacific Rise. This array extends about 400 kilometers off the ridge axis, a little bit more in some places. And then we head down, and you can see all the sites have A at the beginning of them. And then we head off to array B, which instrumented across the Cocos-Nazca ridge. All the different symbols are different configurations of OBS. I'll come back to that later. But as you can see, the goal here was to instrument a long way sort of off axis to get the age maturation of each of these plates, as well as to have some degree of crossing rays that would allow us to measure variations in wave speed, for instance, with azimuth, that can tell us about seismic anisotropy. And then in the region of the CNR, the Cocos-Nazca ridge, sort of nearer the Triple-junction, we have higher station density because we anticipate that there might be small-scale features, both in depth but also laterally, that could be associated with small-scale convective systems near that slow-spreading ridge axis. So that was one of the goals there. An ancillary goal was to fill in a few holes in existing multi-beam coverage. So this was just a map that showed large gaps in any previous multi-beam coverage. And so you can see we did our best to fill some of that in, including some detailed sort of mowing the seafloor mapping in the southeast. So why are we going to mid-ocean ridges? Hopefully most people on this call know that they are the factories of Earth's surface. 70% of the Earth's surface is created at these divergent boundaries, and so understanding them is rather important. They sort of set the condition that then frames the evolution of these plates throughout their age. And despite that, we actually don't know an enormous amount about certainly their deep structure and the processes at work beneath them, and how those processes vary across different contexts of spreading rate and orientation and things like that. So this is just one among many dynamical models produced in the last few years. I know Adina has many of these herself. And this shows the production of a high viscosity plate, the melting at the spreading center itself, and contours of melt fraction. One of the interesting things that we think takes place here is that as melting happens, a relatively hydrous mantle is dehydrated quite quickly as a function of depth, as the incompatible water comes out of the hydrous mantle, goes into the melt, and that means that what you're left with is a much more viscous, much more resistive, potentially restite. Old experiments from Hirth and Kolstad say that dehydration goes with a order of magnitude increase in viscosity, and so we might have sort of a compositional lithosphere, a dry lithosphere, and then also a thermal lithosphere, and these things might be distinct. So these are interesting processes to learn about. In addition, there is plenty of work from modeling and some implications from a previous experiment at a mid-ocean ridge I'll describe in a second, that suggests that the motion of the ridge in the reference frame of the underlying mantle might be quite important to the dynamics. And one of the nice things about this particular triple junction, of which we're imaging two different arms, is that those two different arms have extremely different spreading rates. So it's a little hard to see on this diagram, but this is the Pacific, this is the Cocos, and this is the Nazca on a velocity diagram. This right here, you can see my cursor, right, Adina? Great. This is the Pacific Cocos spreading center, spreading at 126 millimeters per year, full rate. So that's fast. And in absolute reference frame, it's moving a little bit to the west. Contrast that, and I should say that motion is parallel to the direction of spreading. Contrast that to the Cocos-Nazca, which is a very, very different spreading rate, which in itself is interesting. And also that ridge is moving much, much faster relative to underlying mantle, this time to the east, and this time that motion is actually perpendicular to the direction of spreading. So this triple junction in a very small area sets up a really nice natural experiment for trying to understand how these different parameters affect spreading at this particular at spreading centers in general. One of the other things that we are hoping to learn at these two different ridges is how melt is focused to the ridge axis. So there's an abundance of shallow imaging that shows that melt close to the surface at the axial magma chamber or melt lens exists over a zone that's only a couple of kilometers wide, but we think that the melting, if we go back to this figure, the melting actually takes place over a region that can be hundreds of kilometers wide. So it's a somewhat outstanding question how all that melt is efficiently focused so precisely to the ridge axis. And one of the, depending on spreading rate, according to the models, depending on spreading rate, one of the factors that might contribute here is the extent of active versus passive upwelling, or dynamic versus passive upwelling, and the extent to which the actual upwelling of the underlying mantle is focused towards the ridge, associated with downwelling off axis, which of course would change the thermal parameters for the rest of the plate as it ages, because now you've taken mantle close to the surface and then you've actually compressed it again and advected cold mantle downwards. But this would be one way of producing melt much more efficiently close to the axis, as well as a whole host of other methods that could be important in focusing that melt to the axis. Channelization of various different flavors, a compaction boundary that's been suggested for several decades, ideas of pressure gradients, and even the potential for differences in grain size, which itself is a function of stress and indeed strain rate, that might actually contribute towards melt being funneled towards the ridge axis. All of these have been theorized and have been captured in several sophisticated numerical models. But I would argue, and did in the proposal that got this funded, that we have very, very little in the way of ground truth, because we've been to so few ridges to actually try and look at these processes which happen in the mantle deep beneath the surface, to look at these processes taking place. And so, a primary goal of this experiment is to really bring observations a little bit closer to the incredible range of sophisticated dynamical models, theoretical models, and try and understand which among all of these processes are important. I'll also just note that one of these other models, which I like a lot, this is Toby Keller's model from 2017. This also indicates that in some ridges, there may be pockets of melt they don't get funneled to the ridge axis. Right, I was just talking about how efficiently melt does get taken to the ridge axis, but some may never make it to the ridge axis and may be ponded, maybe at the base of a porosity boundary, and that process could also potentially explain all these scatterers that are seen in the middle of oceanic plates by a variety of other imaging methods. And then finally, because we don't have enough science goals so far, we're also interested in the development of seismic anisotropic fabrics, which we think are strongly set at the ridge, and then the fabrics which are extant in the shallower portion of the mantle, those get frozen in because they cool, and then the viscosity increases, and so they can't deform from that point. And then you may have an actively deforming region beneath that the fabrics in the lithosphere, and we are interested in trying to image that process taking place kind of in situ. This is all part of a much broader effort to try and understand the oceans. This is a figure that gets regularly updated by Hitoshi Kawakatsu, showing sort of the Pacific array of arrays. And these swirls are kind of imaginary, and there used to be many, many more swirls on this figure. And gradually those swirls have been replaced by actual experiments. Legacy experiments you can see here are in black dots. Actually, this one and this one were an experiment that I was previously a part of as a co-PI. And then the blue dots indicate current or sort of recently ongoing experiments, and there's ours in highlighted right here. And these add to, just as I mentioned, just a couple of prior experiments that have looked at mid-ocean ridges with broadband seismometers. The most famous and original of which was the MELT experiment in 1998, which deployed these two, one sparse and one dense line of ocean bottom seismometers, and also some magnetotelluric instruments across the East Pacific Rise at about 16 south. And another of which much more recently took place, the PyLab experiment across the mid-Atlantic ridge on either side of the chain fracture zone. This was led by Kate Reicher and Nick Harmon and others. But those two are really the only experiments that have really dedicated broadband ocean bottom seismic instruments to imaging mantle structure to understand ridge processes. And this experiment, as you can see, this also involved a significant component of trying to understand a transform fault and fracture zone. So we have a real paucity of data, and so it's very exciting to be providing, hopefully, huge amount of new data on these environments. As I mentioned, we're in the region of the Galápagos triple junction. And in the original funded proposal, we actually had two more arrays, right? So I sort of described two subarrays across each ridge arm, and we used to have two other arrays. So this is the one that is taking place, just to give you an idea of where that sits within this framework. You can see here, so I should explain, this is the specific rise. Here is the Galápagos microplate. This is the Galápagos triple junction. You can see here is the Cocos Nazca ridge spreading center, which is actually actively propagating westward into this relatively undeformed plate that was just created at the specific rise. This is a fantastically dynamic system. You can see the fact that we have this very different spreading rate manifests in extremely different seafloor bathymetry. It's much more, the abyssal hill fabric is much more pronounced. We have these overlapping, immature spreading centers with less fraction of magmatic opening, more tectonic opening, etc. And so this is where our current experiment is. We actually, as I said, had two other arrays funded, but unfortunately, the NSF had slightly overextended itself, and so quite understandably they decided to reallocate some of their resources. So we actually we're hoping that the previous instrumentation of this region will be great fodder for a new experiment, which I look forward to proposing soon. I don't have much time. I'll just quickly give you a very, very quick flavor of life and operations at sea. We towed a gravimeter and a magnetometer, so we're collecting all this ancillary data. We deployed ocean bottom seismometers. I imagine most people on this call have seen these before. These all come from the Woods Hole Oceanographic Institution OBS Instrument Center. You can see there's various different flavors of flotation, various different types of instruments, and this little table in the bottom right shows all the different configurations, mixing and matching of these housings and sensors to make different types of instrument, some of which are more broadband, some of which are less broadband. This is a movie of a deployment that I don't have time to show you, but we put it over the side. And I can always loop back to this if people are interested in the question answer. Once we have the thing sitting on the sea floor, then we communicate with it and run a survey to work out exactly where it landed. You can read about the method that we developed. It's a relatively old method using two-way acoustic travel times to a transponder mounted on the ship's hull. We added some sort of bells and whistles to this method, and this is the result of one particular station, where you can see the configuration of the survey that we ran. Each one of these dots is one ping, one communication from the ship to the instrument on the seafloor, and you can see we get these very small travel time residuals on the order of milliseconds, and we can determine the location of these instruments to an accuracy of an uncertainty of about 1 meter on the seafloor. That's when it goes well. When it goes less well, then the accuracy is less, but we're still talking on the order of 4 meters. We know exactly where these things are. It's very impressive. As I mentioned, we did some multi-beaming. We tried to fill in some of the gaps in existing coverage. You can see actually where some places have very clearly much more dense seafloor coverage, and some places it looks much smoother. So we added data into those places. I won't describe in detail this. We can come back to this if you're interested, but we found and imaged lots of new seamounts. We were the first people ever to drive over a bunch of these seamounts. I mean, that wasn't by accident. You can see the coarse seamount configuration from satellite CSAT data, and so that we went and did more detailed imaging. They had lots of fun on board. There was all these, lots of birds and sea life, and they saw a giant squid, and whales, dolphins, of course, lots of flying fish, too many flying fish to count. Sometimes the birds come on board. And on the way back, you engage in extra fun things like Deck Olympics and try and keep everything fun. And everyone on board said they had a really, really fantastic time before getting back to land. And so I think that's the end of my time. I don't want to abuse my time slot. So I'll just say that we really look forward to recovering these instruments. We have no idea what the data looks like yet. There have been lots of global earthquakes, which I'm excited about, and we'll see this data in December when we go and recover these instruments. So thank you for the time, and happy to answer questions later in this session.